पीछे तो जगह नहीं दिख रही, पीछे तो बैठ गए सब। बैठ जाओ सेकंड। पीछे का जगह आराम से आराम से आराम से आराम से। मैं क्या कहूँ भाई बैठा तो सालियाँ निकल आई ललक है मेरे ये पीपीटी देख लेते हैं अपने पास पीपीटी देख
हाँ उनको पता है, उनको पता है ना। हाँ पता है। बुके प्रिंसिपल सर देंगे, हाँ वो देंगे थोड़े टाइम, प्रिंसिपल सर देंगे वो तो देंगे। पहले भेजा एक उससे पहले तो अभी देंगे, अभी प्रिंसिपल सर देंगे, मैं स्किप भेजा हूँ, स्किप कर देता हूँ।
A very warm good morning to everyone present here. Respected Principal Sir, our distinguished speaker Dr. Swami Siddhanta, senior members and all my dear friends. I, Adit,
And I, Ritika,
heartily welcome you all to the inaugural lecture of Science Conclave 2025.
it is truly a great pleasure to announce the 50th anniversary of the Chemistry, Mathematics and the Physics Society of St. Stephen's College, marking 5 decades of excellence, curiosity and scientific discovery since their inception in 1974.
On this auspicious occasion, I would like to call upon Dr. Jaspreet Paul, Staff Advisor of the Mathematics Society, to share a few words.
Respected Principal Sir, esteemed faculty members, distinguished guests, and dear students, a good morning to everyone. It is both an honor and privilege to welcome you all to this Science Conclave and Golden Jubilee celebration of Mathematics, Chemistry, and Physics Societies of St. Stephen's College. This gathering marks not just the celebration of 5 decades of academic excellence and intellectual pursuit, but also an affirmation of power of science to shape our future. Today, as we stand together to commemorate this Golden Jubilee, we reflect on a journey that began 50 years ago. A journey that was founded on curiosity, inquiry, and relentless quest of knowledge. Over the decades, our 3 societies, mathematics, physics, and chemistry, have not only cultivated scientific thought, creativity, but have also inspired generations of students to explore the vast interconnected world of science. The society, since their inception, have been more than just academic hubs. They have been platform for collaboration, innovation, and dialogue. The countless discussions, debates, workshops, seminars, and projects that have emerged from this space have allowed us to engage with some of the brightest minds, not only within our college but beyond these walls. As we celebrate the legacy of past 50 years, we also look forward to the future, a future where we continue to push the boundaries of knowledge, embrace new challenges, and drive the solutions to problems that confront humanity. This conclave aims to create an environment that encourages thinking, scientific inquiry, and exchange of ideas. It is such exchange it is in such exchange that innovation is born. And it is here that we lay the foundation of the next 50 years. As we embark on this exciting journey, I would like to extend my heartfelt thanks to everyone who has contributed to organize this event, staff advisors, senior faculty members, and of course students, whose enthusiasm and dedication continue to inspire us all. We are also fortunate to have with us today guest Dr. Somanik Siddhanta from IIT Delhi, who has generously agreed to share his insights and experience with us. Your presence is a great honor, sir, and we look forward to your invaluable contribution to this event. Before we proceed with the inaugural ceremony, I would like to share a thought by Einstein. The important thing is not to stop questioning. Curiosity has its own reasons for existing. As we delve into the world of science, may we continue to question, explore, and seek answers. Together, let us make this golden Jubilee celebration, a memorable event full of inspirations, discovery, and learning. So with this, I formally welcome you to this Science Conclave and Golden Jubilee celebration. May this event be the beginning of more intellectual growth, discoveries, and collaboration. Thank you, and
Thank you, ma'am, for sharing your invaluable thoughts.
Now, it's time to take a journey down memory lane, for which I would like to invite Advait Raizada from Second Year Mathematics Honours to highlight the rich legacy of our society.
Respected Principal Sir, distinguished faculty members, esteemed guests, and fellow scholars, it is both a privilege and a profound responsibility to address this gathering on the momentous occasion of the golden anniversary of the Science Societies at St. Stephen's College. This commemoration not only acknowledges 5 decades of rigorous academic engagement, but also reaffirms our commitment to intellectual curiosity, empirical rigor, and the pursuit of knowledge that transcends disciplinary boundaries. Our beloved college, with its rich heritage and unwavering commitment to excellence, has provided fertile soil in which these societies have taken root and flourished. The distinctive Stephanie ethos, that peculiar blend of intellectual rigor, moral fortitude, and societal responsibility infuses the work of our science societies, giving purpose to their pursuit and meaning to discovery. As we stand at the golden threshold today, looking back upon 50 years of achievement and forward to 50 more of promise, we honor not just the abstract principles of science, but the very concrete legacy of the mathematics, physics, and chemistry societies of the St. Stephen's College. This legacy of the Mathematics Society is inextricably linked to the visionaries who fortified its intellectual foundations. Dr. S.K. Gupta, whose inquiries into the irrationality of mathematical constants, E and pi, underscored the elegance of abstract reasoning, and Professor S.R. Nagpal, whose commitment to scholarly mentorship endures through the Nagpal Fellowship. Their collective efforts reaffirm that mathematics is not merely a system of computations, but an evolving philosophical and analytical language through which we construct our understanding of the universe. Parallel to the mathematical odyssey is the trajectory of the Chemistry Society, which, upon gaining autonomy in the 1970s, established itself as a nucleus of chemical inquiry and experimentation, under the stewardship of pioneers such as Mr. G.R.V. Subramanian and Dr. D.P. Goyal. The Chemistry Society has cultivated an environment where theoretical postulates converge with empirical validation. Its initiatives, ranging from high-impact guest lectures and research colloquia to hands-on experimental workshops, have bridged the chasm between foundations and chemical theories and their tangible applications in contemporary scientific challenges. The Physics Society has for half a century transcended the ordinary boundaries of classroom learning, creating instead a living tapestry where minds of all stations, students, faculties, and distinguished scholars alike have found common ground in their wonder of the physics story. In our commemorations, we honor those whose names now grace our most cherished traditions. Dr. R.K. Pokley, L.A. Meera, Ranjan Roy, and Professor S.C. Bhargava, whose mentorship shaped countless minds and whose legacy endured in the research fellowship awarded to our most promising scholars. As we commemorate half a century of these venerable institutions, we are not merely making the passage of time, but reaffirming the principles that have propelled us forward, an insatiable quest for knowledge, a commitment to cross-disciplinary collaboration, and an unwavering dedication to scientific truth. This anniversary stands not only as a culmination, but also as an inflection point, a moment to galvanize future generations to uphold and expand upon the intellectual legacies of these societies. As we look forward to the next 50 years, let us strive to push the frontiers of our disciplines, to interrogate the unknown, the boundless universe, the relentless curiosity, and to shape a future where scholarly inquiry remains boundless. With hope in our hearts and God overhead, may the torch of knowledge burn ever brighter, and may our collective pursuit of the discovery continue to illuminate the path ahead. To conclude in William Shakespeare's words, ignorance is the curse of God, and knowledge are the wings wherewith we fly to heaven. God help.
Thank you, Advait, for shedding light on the legacy and journey of a society.
Moving on, light is a symbol of brightness and prosperity as it expels the darkness. For the auspicious ceremony of the lighting of lamp, I would like to invite our respected principal, Professor John Gondis, the Dean of Academics, Dr. Maria, the Registrar of Societies, Dr. Amrita Turika, the Head of the Mathematics Department, Dr. Archana Chopra, the Head of the Chemistry Department, Dr. Prabha Sharma, and Dr. Sanjay Kumar from the Physics Department.
अच्छा ओ
Now, I would like to request our principal, Professor John Bobby, to present a bouquet to our honored speaker, Dr. Soumit Siddhanta, as an expression of our gratitude. And I would also like to request Principal Sir to enlighten us with his words.
Good morning, everybody. Respected and distinguished Professor Soumit, our chief guest for the day, my esteemed colleagues, both young and senior, my dear junior members. College is 144 years old, and the departments of mathematics, chemistry, and physics are 50 years old. Today, we are celebrating the golden anniversary of these three departments. But when the college is 144 years old, and the science, so-called science departments are just 50 years old, what was happening between 1881 and the 70s when the science department was started? I think that was a period of gestation when a lot of ideas were fermenting in the minds of those in college. I want to make use of this analogy and ask each one of us, especially our junior members, to consider a time of reflection when you will be able to push your innate curiosity along with the scientific principles that we have here through these departments and through other interactive philosophical discussions, lectures, activities, both here and outside the college, so that not only as an academic institution, but as a nation, we will be able to revive this interest in promoting a scientific temper. That's very important for us, because when all kinds of ideas are being exchanged, some of them very unscientific and harmful, it is important to bring the light of reason into our innate curiosity. And that is where it is important for departments like chemistry, physics, and mathematics to take us forward, along with other departments like philosophy and computer science. So today, when we are celebrating 50 years of good work, I want to place one idea which I've been repeating for the past couple of years. It's not enough if we have events like that. We should have proof of our scientific temper and proof of us having applied our minds combined with our curiosity to come up with discoveries which make a difference to men and women across the world. Science should be put to the service of mankind. In July last year, I was traveling with a group of vice chancellors to Israel, and we visited 3 universities. was so overcome with the universities there and with the kind of work that they were doing. Each of the three universities, we have traveled to Tel Aviv, Ben Gurion, and one more university, I forget the name. And each university was vying with the other university to get a Nobel Prize. And each of those universities had at least 2 Nobel Prize recipients. And when I came back, I was thinking, a little unhappy, asking myself why we did not have a Nobel laureate as yet. We are an undergraduate institution. You may think that we are not equipped for a Nobel Prize, but this is where I want to place this thought before all of us. The period of gestation, which I refer to, between 1881 and the 70s, that is when a lot of things were happening which led to the creation of your 3 departments, our 3 departments. And because of our 3 departments, many of us are here, many of us have benefited. So in a similar manner, what we do here should push curiosity, should push the scientific temper. It doesn't matter if someone from this college who is currently here does not get a Nobel Prize. But if one of our students goes on to any institution, anywhere else, and because of what was given here by the teachers, by events like this, if that student gets a Nobel, then we should be happy. And I know that it is not impossible. If we determine, it can be made to happen. So I leave that thought with all of us today. The Nobel Prize, I'm not too bothered about the money. Money is not the important thing. The fact is that the Nobel is a benchmark of a discovery or an event or a scientific achievement or a literary achievement which is of a global nature. And that is what our aim should be. Our aim should not be here. Our aim should be up there. And that is what we should strive for all the time. As you go about your adventure, that's the title of what you're going to do. As you go about this adventure, I'm going to request each one of you to extend this adventure beyond the stipulated 2 days. 2 days, correct? 1 day, 1 day of it. Beyond the 1 day. And take it all through your life. God bless and be with each one of you. May you increase in your knowledge. May you be very, very curious. And may that combination, the scientific temper and your curiosity, lead us to a better world. Thank you very much.
Thank you, sir, for enlightening words.
It's my immense pleasure to introduce Dr. Somit Siddhanta, our distinguished speaker for the inaugural lecture of Science Conclave 2025.
Dr. Somit Siddhanta is an associate professor in the Department of Chemistry at IIT Delhi. His research focuses on the plasmonic, nanopore, and label-free vibrational spectroscopy, driving advancements in biological imaging, diagnostics, and manipulation. Dr. Siddhanta pursues postdoctoral research at the Johns Hopkins University and was a research associate at the Purdue University. He completed his PhD in material science from GMCSR, Bangalore, after his undergraduate studies at the University of Delhi. During his PhD, he was part of the BSF Germany talent pool.
With over 50 publications in international journals and lectures at prestigious conferences, He leads the nanoscopic imaging and sensing lab at IIT Delhi, mentoring PhD and postgraduate students. His contributions have earned him accolades like the IUSSTF Research Fellowship, the American Society for Laser Surgery and Medicine Research Grant, and recognition as an emerging investigator by the Journal of Materials Chemistry Week in 2023. Sir, we are extremely honored to have you here.
Sir, we are extremely honored to have you here with us today. In today's lecture, Dr. Soumik Siddhanta is going to enlighten us on the topic Raman spectroscopy or vibrational adventure. Without further ado, let us commence the lecture. I now invite Dr. Soumik Siddhanta to address the gathering and enlighten us with his lecture.
Hello. So, good morning everyone out here. I think all of you are enjoying this conclave already, and I would like to thank Varghese, the presidents of the societies and all the faculty members here for inviting me on this momentous occasion of golden jubilee of all the three of your societies. So it's indeed a very special occasion, and I'm really honored to be here and speak about something which is very close to my heart, which is very close to my research area, and also which is very, very important in the context of our country. Okay, so we are here to, today also it's the National Science Day. So can you tell me, anyone, like, what are we here for? Like, what is this National Science Day? Anyone? So we can keep it a little interactive, okay? Otherwise, let's not make it a very boring, like, lecture kind of thing, okay? Yeah, it's actually not his birthday. So his birthday is on November 7th. So this is the day when he gave to the world the Raman effect. Okay. So how many of you have heard of Raman effect? Have studied here, have used Raman spectroscopy? Okay. So some of you have used it. So it's amazing. So can you tell me the connection between Raman and the Mars rover, for example? Do you see any connection here? Okay, so one of the Mars surface, right? So it's pretty amazing. Like something which has been kind of discovered 100 years back, almost 100 years back. So we are going to celebrate the 100-year centenary celebrations for the Raman effect in 2028, and it's going to happen in Kolkata, the birthplace of Raman. Raman's spectroscopy, Raman. Okay, so it's pretty amazing journey, and how Raman is still relevant, and it's still emerging. New things are done using light scattering and Raman spectroscopy. So it's pretty amazing. Okay, it's kind of like a timeless discovery. So I'll talk about today. I'll talk about the life of Raman. So why I chose to talk about the life of Raman? Because his life is like a life of ideas. So if you see the life of Raman, so you can see how his ideas generated forward, and how it led to the discoveries, and how it led to the emergence of basically the science in India. So you might not realize that this thing, but his contribution to Indian science is pretty immense. Okay, so I will take you through this journey and show you how his ideas basically emerged, and I will leave you after that to think like what we can do, what we can take from his life, and what we can learn from his life to do much better. Okay, so bit of introduction. So I think we already gave a very detailed introduction. So I come from IIT Delhi. My lab and office is somewhere on the 6th floor of this main building. Many of you might have been familiar with this. And this is our UG lab for undergrads, chemistry lab. Okay, so all of you are welcome to visit IIT Delhi, visit my lab. And today you can stop me anytime, ask questions. Be curious. Okay. so. So today we are celebrating the National Science Day. So February 28th is very special. So it was on this day Raman effect was discovered. The first celebration actually took place on February 28, 1987. Okay, so the government of India wanted to make it a day to celebrate science and the achievements of C.V. Raman. And this effect was first observed by C.V. Raman and his students, okay, Venkataraman and K.S. Krishnan, okay, two pillars of the discoveries behind this Raman effect. And just after 2 years, he went on to win the Nobel Prize. So this is one of the shortest time periods between the discovery and winning the Nobel Prize. This is pretty amazing, right? But there are reasons for that. Okay, it didn't happen overnight. Okay, so it's a process. Okay, so discovery was a process. So the Nobel Prize was also a process. It didn't happen like, okay, he didn't discover it on this day, okay, and at 2 years he got the Nobel. It's not like that. Okay, it's completely different. Okay, so these are the references from which I took a lot of things for this lecture. So these are very nice books on Raman and his life. So in between you see it's a pictorial biography written by his nephew. In fact, it's very amazing book. So you can download it from internet. Okay, so yeah. So one thing I wanted to tell you that. I think all of you have heard about Srinivasa Ramanujan, right? He's the most famous mathematician that India has produced, right? So he was kind of contemporary of C.V. Raman. So how many of you knew about this? Okay, so but we lost him very early, so he died really at a very young age. But at that time, scientists around, the mathematicians in US wanted to make a statue or a bust of Srinivasa Ramanujan. Okay, such was his influence. Okay, they wanted to make a statue of him. But one of the astrophysicists that time in US actually he said that if you are building a statue of Ramanujan, you should also build a statue of C.V. Raman. Okay, because they are the two Indian geniuses. Okay, equal footing. So that was the kind of recognition that C.V. Raman had at that point of time. So this is a short, the flow of my talk. So I will be talking about a bit of C.V. Raman, his education, how the Raman effect came into being, then what he did in Bangalore, and the applications of the recent applications of Raman spectroscopy. I will touch upon, including some of my own research on this. Okay, so he was born. C.V. Raman was born in Tiruchirappalli in Madras Presidency in November 7, 1988, and he did his BA and MA in physics from Presidency College, Madras. Right. So you see here that so this is Raman, with his family. So this is young Raman here. And this is with his friends in Presidency College, and this is his wife, Sundari. So these are some of the old pictures which I got from the archives. So if you see this, so he did his MA and BA. So it's a Master of Arts and Bachelor of Arts. So those times they also had to read about literature, English literature. So Raman was so he read a lot of English literature, and he was very good in writing English. Okay.
So till now he has around more than 450 research papers, and the hallmark of these papers were they were written in very good English. Okay. So well beyond the capability of normal Indians at that point of time. Okay. It was super, very lucid, very crisp. So I think his degree, his education played a big role in that. Okay, and so during his undergrad, like all of you sitting here, it was in 1906. So how old was he? 1888 to 1906, 17, 18, right? And he was in Presidency College, which had no research infrastructure. It has some basic labs, even UG labs. From that lab, as a UG student, he wrote his first paper. Okay, this was his first paper. The title is, Unsymmetrical Diffraction Due to Rectangular Aperture. At that point of time, okay, when all the young double-slit experiments and everything were just being developed. In a simple UG lab, he did his experiments, and this was actually very significant finding that time. And you see, it's a single author. He did everything himself. There was no one else, in this paper. It was a single author paper. Okay, and this was actually very significant because the diffraction, okay, from asymmetrical states or rectangular states is very important to understand diffraction from crystals, for example, which developed much later in 1920s. Okay, when Compton and all got the Nobel Prize. So you can understand his first paper was, as a kid, as a student, and you can see he looked like this kid in 1906. Yeah. Now, can you tell me? Can you guess what was his second paper and when it came? Okay, so this was his second paper, came the next year. So this was, he found a way to determine the surface tension of liquid using the curvature method. Okay, and he published it with a lot of mathematics. He used a simple optical microscope, very nice imaging, very nice image analysis at those times, very nicely written paper. He communicated with this paper. Okay, and nowadays you see, after all this, information all around, we still how many of us know how to submit a paper? Forget about writing about it. Okay, so there was nothing there. There was no internet. There was nothing. There was no one around him who even did research. So how did he do all these things? That's what Raman was. Something like once in a generation kind of person. So what happened when he communicated the paper? This paper was seen by Lord Rayleigh. How many of you have heard about Rayleigh scattering here? Elastic scattering, right? So that time, Rayleigh was studying about sound waves, like how our ears perceive sound. Okay, and then he saw this paper, and then he communicated with Raman and called him a professor. He didn't know. And that time Raman was just 18. He was just starting out his master's, right? Pretty amazing. So can you tell me, did Raman do a PhD? No. So Raman didn't do a PhD. Okay, Raman didn't even have a PhD. So, anyways, so such was his brilliance that he was told to go to England by his college professors, and there is a story, okay, like why he couldn't go to England, because he was not medically fit. He was a fragile guy. The doctor told him that you will die of tuberculosis if you go to England at that time. And he credits that medical officer till later, later in his life, that he kind of saved him, because if you had gone to England, he would have been a civil servant instead of being a scientist, right? Instead of having the life he had. Okay, and this is some of the letters which Lord Rayleigh wrote to Raman in 1906, 1907. I couldn't make a single word, but maybe you can. Okay, but it's pretty nice at that point of time. So, sorry. So now, after his masters, he had to do something, right? So his brother was in civil services. Raman was a very bright student, so he wrote the civil service exam. He topped it easily. Like, he was one of the highest, rankers there. And then then he got married. Okay, pretty young age. So can you guess how much salary he used to get as a civil servant that time? It was 1400 rupees a month, which was huge that time. Huge. Okay. His father used to get 80 rupees comparatively as a salary, as a professor in Madras. So, but there is a joke. Okay. So his wife. So he was something different. Like there was a lot of anecdotes about how he, arranged his own marriage, which was against the custom at that time. And then his wife also kind of jokes that government employees used to get like 150 rupees extra if they were married. So he kind of married for the money. So that was kind of a joke, but of course, like Lucas was one of the figures behind his life. So, but the thing is, they used to stay in Kolkata, Calcutta that time, as you know, and he was very impressed by the Indian Association of Cultivation of Sciences here. Okay, so that was set up to cultivate science. So nowhere else you will find this word, cultivation of science. So that was the vision of Mahendralal Sirkar at that point of time. So he was very impressed, but nobody was doing anything. The labs were there, but nobody was doing any research. So they agreed to let Raman work in the lab. So what he did was he used to get up 5:30 in the morning, go to the lab, work till 9:30, come back, change, wash, go to his office, be there, do his civil servant job till 5, then again back to his lab till 9:30 at night. And on Sundays, it was full day in lab. Not a very interesting life for a new couple. But that was it, so within 3 years, he converted that lab, that space, that thing, into one of the best happening research areas in the entire world. That ICS, within a span of 3 years. Okay, can you imagine? Okay. So that time, he was also helped by Ashutosh Mukherjee. He was also called the Tiger of Bengal. That time he was very influential. So then he was chosen to. He was doing a lot of research. I will show you very fascinating research that time. And then he was chosen to be the Palit Professor of Physics, which is a very very prestigious position at the time. But the board was opposing because he didn't have a PhD degree. Right? How can he take students and become a professor if he doesn't have a PhD? So Ashutosh Mukherjee actually arranged for him to get an honorary degree from University of Calcutta, and then he became a professor. He never studied abroad, so but he got an honorary PhD degree. Okay. So now, what really happened from 1906 to 1917 in Kolkata? Okay. So, do any of you know that he was one of the world authority on sound and music instruments? Do any of you know here? That time, okay. This is his papers. These are some of his papers, and papers published in Nature type journals, very top journals that time. So he investigated a lot of instruments. Okay, like for example, the veena. Okay, so when you play the veena, it has some harmonics which is so soothing to ears. So he tried to find out, is just our psychological effect, or is there something in the sound itself, like some science in the sound itself? Okay, and then he actually found it. Okay, he found what are the harmonics, what are the particular harmonics which makes it so soothing to our ears. Okay, so these are that time, like Raman's father played very good violin, so he had that kind of questions in his mind, right? And then he also studied ancient scriptures, sculptures, and found out what kind of instruments they used. Okay, so kind of instrument out of it. Okay, like a sonometer. We created a sonometer out of, like, by learning how the workings of it are. Okay. He was also very interested in acoustics. Okay, so he, when he went abroad, he went to St. Paul Cathedral and studied the whispering gallery modes. Have you heard of the whispering gallery modes? You know, the sounds travel in circles. So there are certain focal points in the room which can hear your sound, but nowhere else. So it's in the ballroom bars, basically, in India. Okay. So he did a lot of studies in that. So what can you understand? That he had a very innate interest in waves, be it sound waves, be it light waves. Okay, so we're coming to scattering, right? So we know what is his background now, right? So he also did a lot of study on the acoustic instruments, other percussion instruments. So here is the tabla. So he found out that they make a thick layer inside, okay, and on the skin, on the leather skin, hollow leather skin, and then adding this thick layer inside, it creates different kind of harmonies, okay. And so he published all of this research in journals, okay. Now another thing is the waves, okay, the sea. So unknowingly, the sea actually played a very important part in the Raman effect. How? Because when he was a kid, their English teacher used to teach by the seaside. Okay, so he had a majestic view of the sea, and English he was learning, right? So later we'll be able to see. So this he wrote about his experience in some of his memoirs about that. So so he started his own journals from Indian Association of Cultivation of Science. And ironically, he himself used to publish in those journals because nobody else was doing anything else initially. But now these journals are still there. Okay, Indian Journal of Physics and all. Okay, these are still there. Okay, so one important event of his life was Sir Ashutosh actually told him to forcefully ask him to go to Europe in 1921. And there, he actually met very famous scientists like J.J. Thomson, Rutherford, Bragg. You have heard all these names, right? Thomson, Rutherford, amazing scientists. Like all our textbooks are made because of them, right? So they had to cross the sea, okay. And when he was coming back, the beauty of the Mediterranean Sea and the scientific questions it posed shaped his research area. So you think, how is it? Okay, you remember Lord Raleigh. So he said that time he found out, he gave a Raleigh scattering, right? Like, scattering is inversely proportional to lambda over 4, all of you know, right? Mm-hmm. So he said that the color of the sea is blue because it's a reflection of sky. And he said why the sky is blue. Right? Raman didn't agree with that. So he took his instruments to Europe, and his experimental instruments were there on the ship with him. He didn't agree. He said there is something is there in the water itself. Okay. So he was running all around the ship, taking water samples from different depths of the sea and analyzing it using ecoprism. So he found out that there is some inelastic scattering happening from inside the water itself. So nowadays we know, right, the sea water is blue, right? So he said that an interesting possibility that should be considered in this connection is that refracting particles may at least in part be the molecules from the water itself. Okay. So he said that the water molecules can diffract because people were that time fixated with diffraction from solids, like how X-ray diffraction happens in solids, but nobody was looking into liquids. So when he came back to Calcutta that time, so he focused on these three research areas, like the scattering of light by liquids, scattering of X-rays by liquid, and viscosity of liquids. Focused his research on that. So then he said that when we study X-ray crystallography, X-ray scattering, how many of you have studied X-ray scattering here? maybe not much. So if you put a light or any radiation whose wavelength is similar to the crystal lattice spaces or distance between the atoms, so they diffract. Okay, it gives diffraction patterns. So the diffraction pattern what you get is a reciprocal space. Okay, so now what is a reciprocal space? You will read later in your solid state chemistry or physics, right? So people used to get experimentally that diffraction pattern which is in the reciprocal space or the frequency space. So if you convert the time domain into frequency domain by doing a Fourier transformation, you get the frequency space, right? Or the reciprocal space, because everything is 1 by A, right? Opposite, right? So mathematically you could arrive at the Fourier space and also see it experimentally. So people were studying that using X-ray crystallography, but Raman said that we can do this in liquid itself, and he published the Raman Ramanathan paper in 1923. Okay, and then he also did this light scattering instead of X-ray scattering in 1923. Compton did that and got Nobel Prize in using X-rays, and he got Nobel Prize in 1927. Can you imagine? So he has that contribution also. He was way ahead of his time. Okay. So now the all-important Raman effect, how it came to be. Okay. So that time, it was the emergence of quantum mechanics. That time Einstein had the photoelectric effect discovered. And then Maxwell and Hertz and Max Planck and Einstein. So they gave the dual nature of waves, right? It's either waves or particulate nature, right? So Raman had a very interesting insight that if scattering of light is considered as a collision of light quantum with a molecule, many concepts derived from the classical wave theory will be violated. Okay, so this was before the birth of quantum mechanics. He postulated this. Pretty amazing, right? The quantum mechanics is emerging and he is working with light scattering, which has direct implications with quantum mechanics. That time. Okay, so there was a lot of papers being published, discussions going around the entire world. So for the next 6 years, from 1917, he actually fully immersed himself in the study of light scattering. Okay, so now what happened was on February 28th, so the students did an experiment. Okay, so I think all of you will be able to relate with this experiment. So he took a prism. So what can the prism do?
Dispersion.
It kind of disperses. So it's a dispersing instrument, right? So it kind of scatters, disperses all the wavelengths, right? So now, what his student K.S. Krishnan he did was he took white sunlight, right? And he used a violet filter. Okay, maybe it's just a diagram here, but he used some mechanism to separate a particular wavelength of light, and then he had a liquid. Okay, so this light fell on the liquid, and then he collected the light emerging from the liquid, and he saw that there is a violet light, but there is also a green light. So he used a green filter to block out this violet light, and he could get the green light. So you are putting a light, but you are getting some light which is different. Okay, so this was very interesting that time. Okay, so so why this was interesting? Because people were thinking this was fluorescence. You know fluorescence, right? You know the Jablonski diagram, the emission and the fluorescence. He said, why? It can be a weak fluorescence. But then Raman proved that this light which is coming out is polarized. So when can light be polarized? It can be polarized when it gets scattered. So it's a scattering phenomenon which is happening, not a absorption and emission phenomenon. Okay. So, and he was a brilliant experimentalist. So he did all these experiments with sunlight. Okay. How, because sun moves, right? How will you get a constant value of the intensity of light in inside your lab. So he actually made a heliostat. So what is a heliostat? So he put a mirror outside his lab and a small hole in his lab where the sunlight came. So he connected this mirror to a clock. Okay, so as the sun moved in the horizon, so his mirror moved and the light came. So he used to get the same intensity of light inside his lab. He made this, okay. Then he made his own filters, he made his own, spectrometers and how to observe light. Pretty amazing. He was one of the best, experimental physicists at that time. It's not easy to do. So this was his spectrometer, which he used to, discover the Raman effect. And these are the photographs. Okay, so you see these lines. So these are the shift of the frequencies, basically, from the Rayleigh. Okay, so two things you have to remember. So this was an effect, and he knew that he was jumping around. Okay, he knew that he had discovered something. Why? Because that time, Kramer and Heisenberg, two great names in European physics, they developed a theory of collision or aspects of collision, of quantum particles basically. And based upon their papers, Heisenberg went on to invent the field of quantum mechanics. And that time Raman effect came. So they lapped up this effect because this effect could explain a lot of phenomena in quantum mechanics. So basically Raman is the second order perturbation theory. If you have studied perturbation theory in your quantum mechanics yet, so it's a direct example of that. Okay, so he was, you see, quantum mechanics was rising in Europe and US, and he discovered Raman effect here. This is a direct experimental observation of the quantum mechanics. So then what happened was, Max Born, for example, and everyone, they said that Raman discovery in its entirety, is predicted by quantum mechanics. Okay, and see, this was the night of the discovery. At 9:30 at night, Raman came to, their room, K. Station's room, and they were like having their dinner and all. Then they said, this is one example of, Kramer-Heisenberg principle. Okay, he's so excited. Okay, so then this something very significant happened was Sommerfeld. Sommerfeld. How much time? So Sommerfeld you have heard, right? So he visited India. Okay, and Raman demonstrated this effect in his lab to Sommerfeld. So he saw this, and he was one of the greatest scientists in that time, most influential scientist, right? He was also very close friend, became a very close friend of Raman, and he suggested his name for Nobel Prize later. So he said, was thinking of the spectroscopic effect discovered Raman, which likely, like no other discovery, attracted attention and scientific cooperation all over the world. So you remember, so it's like all the quantum physicists in the world are like looking into Raman's discovery at that time and identifying, such an important discovery. So then he went and met a lot of people, discussed the science, discussed the effect, with Compton, with Wings World Institute in Denmark, this is with Heisenberg. Okay, so the world was in awe of his discovery. Okay, and the amazing, the very simple instruments he used, right? Amazing, right? So he said that it was not a weak fluorescence, it was scattering. It was matching with the quantum chemical calculations. It was matching, So at that point of time, so amazing, right? So how many of you know that scattered light is polarized? Did you know? How many of you use DSLR here? Okay, so if you use DSLR, use a polarizer. Why do you use a polarizer? Use a polarizer, right? Thin lens you put it down. Have you thought like why use the polarizer? Okay. Okay, so this is a DSLR image. So this is using the polarizer and this is not. So the reflected light or any emitted light is not scattered. It's not scattered light. Reflected light can be blocked by a polarizer. But scattered light is polarized, so you get one plain polarized light coming through it. So the polarizer basically rejects the reflected light. So it's pretty. This we all know now, right? Yes, absolutely. Absolutely. Now we know the physics, right? Now we know the chemistry behind it.
A particular orientation also.
Yes, absolutely. But can you now imagine where it came from and how everything is connected, right? So after his Nobel Prize winning paper, okay, scattering of light. What was the paper which came next? Nobody asked this question. Like, he published the Nobel Prize winning paper, right? But what was the paper after that? That was on the polarization of the scattered light, Raman scattered light. This was the paper. It's one of my favorite paper. One-page nature paper. You should read the English here. It's not legible from here, maybe, but you should. So you see this image. So these are spectrographs. So you see the top panel and bottom panel, top panel, bottom panel, top panel, bottom panel. So this is the scattering from one particular orientation, and this is the scattering from another particular orientation of the polarizer. So that means what? The scattered light is polarized. The intensity depends upon the orientation of the polarizer. Beautiful experiment. And this same thing was observed by Compton using X-rays. So he was trying to find a correlation between X-rays, which was being discovered by Compton, and his effect. So you can see from how many different angles he was trying to tackle his thing. Huh? So his discovery came in the news. So these were some of his students who were involved. And one interesting story I should share that Compton, right? Not Compton. If you see is Sommerfeld. When he visited Madras, okay, he saw Raman's discovery. He also met a very fine young Indian scientist, S. Chandrasekhar. You know, he got a Nobel Prize too, but he was a US citizen, right? He discussed many theories with Sommerfeld that time, which actually helped him in his Nobel Prize discovery. So you can understand, like, talking, interacting with scientists in a global stage, exchanging knowledge is very important. The connections you make, you have to make right connections. Okay, so that is like absolutely necessary. Okay, so this was Raman receiving the Nobel Prize in Stockholm. But another anecdote is when he came back from England in 1926, Ashutosh Mukherjee asked him, what next? He said, Nobel Prize, of course. Still not published his paper on Nobel Prize that time. And after his paper, before the announcement of Nobel Prize, he had already purchased his tickets to Stockholm. He reserved his seat on a ship to Stockholm. It was like crazy, right? Yes, so it was amazing. It was like amazing. I mean, I cannot even explain this kind of thing, right? Who knows who gets Nobel Prize? Absolutely, it's a very tight secret, right? But such was his confidence and, like borderline audacity, I'd say. Like, it's pretty amazing. Okay, so then after the Nobel Prize happened, he went to Bangalore as a fourth director and the first Indian director of Indian Institute of Science in Bangalore. He was also an entrepreneur. How many of you knew that? He opened a company, Travancore Chemical, and then he used the money from his company to fund his research. That time. Okay, Pretty amazing. Then he retired from IISc. He couldn't stay in IISc long because he was a very strong-headed person. He was at loggerheads with admin most of the time, so he left. Then he made his own institute, Raman Research Institute, which is still there, doing very well. And then he served there till his death. Okay. So, very nice story. But now, where do we stand? Okay. I said that Raman has traveled to Mars. It can actually, there are a lot of variants. You see here, cars. What is cars? Faster cars. Cars is coherent anti-stroke RAM. A lot of variations of Raman has come. It has been used to detect even a single virus particle like COVID. It is kind of can be used in surgery. So this is a Raman probe from where the laser comes. It is used in brain surgery. It has been shown to because it gives real-time information about molecular vibrations, right? Molecular identities, right? So during brain surgery, you cannot cut off the entire tissue, right? You lose some function. So you need very precise information. Okay, so Raman spectroscopy, as you know, has been studied in books. It's a scattering phenomena, and then it can be also explained using a classical oscillator model. So it is very important because it makes it easier to understand. Isotope leveling, for example, it shifts the frequencies. So many experiments can be done. Then it has a lot of features. You can use lasers, different wavelengths of lasers, which can penetrate to different depths. It has very sharp spectra. So this is the Raman spectra of cholesterol, not my favorite molecule. Okay, so you see sharp features of bonds, right? There are different bond vibrations, which forms a fingerprint of the molecule itself. Right? And these are some of the bond vibrations which has particular frequencies. So now we know that the scattering comes from the polarizability of the electron cloud in a particular bond, right? So when the light comes and then there is a change of polarizability, then the vibration of this electron cloud produces its own radiation, which is kind of like the scattering, right? So that's why the scattering is always polarized, okay? Because it happens because of the fluctuation of polarizability inside a molecular bond. So you have studied all this. So this can be explained, through the conventional expression of induced dipole moment, and alpha is the polarizability. So you read this in your textbook. So important thing is that the change of polarizability is very important. So we do a Taylor series expansion. Now, why do we do a Taylor series expansion? Why not do a Fourier series? Why not do a Maclaurin series? Any mathematicians out here? Okay, think about this. Okay, why do we do a Taylor series expansion of polarizability of a bond, not Fourier series or Maclaurin series? Okay, think about this. Okay, you don't find this in textbooks, but if you want to discuss with me later, okay. So I need to rush to get now because I think okay, I don't want to. Okay, so you see the change of polarizability in a vibrational CO2 molecule. Okay? So those vibrations where the change of polarizability can be seen, that will scatter the light. So those modes where the polarizability changes with time, you see those modes in the Raman spectrum. Yeah, this is what you read in the textbook. Okay. If you have a three-dimensional molecule, you have normal modes of vibrations. So basically, you can show this polarizability in terms of Raman tensors. So mathematicians here, what are tensors? What is the difference between a matrix and a tensor, or a vector and a tensor? Any answer? Read about this. Okay, so okay, so polarizability tensor. So Raman is a tensor. So you see there are 9 normal modes of vibrations, like vibrations present, and there can be only 4 kind of vibrations which changes the overall polarizability of the molecule. So those four bonds, like these three and one. So you see these peaks coming up in the real experimental ground. Okay, so it's all about change of polarizability. So how will you understand in the three-dimensional molecule? You have to look into the structure. Okay, you have to look into the group theory. Okay, and then you have to deduce the Raman tensor. So these are some kind of things you will read. But I'm not going into the textbook stuff. I'm just giving them a flavor. Okay, what you should study. Okay, so now, of course, like the scattering, we can also think in terms of electrons. Like the scattering takes place from a virtual state, basically. So it goes from one vibrational level to another vibration level. So it gives rise to little exchange of energy with the vibrating polarizability. Okay, so it's like you have a vibrating drum and you throw ping pong ball on it. So either the ping pong ball comes back with the same frequency, same speed, or it can dampen, or it can gain more speed. Depends upon how it strikes this change of the polarization cloud is kind of fluctuating. So it depends, like if the electron, what kind of, like whether the electron will gain energy or lose energy, or the energy will be same, right? So based upon that we get the Stokes or shifted scattering. So sorry. So this is, I'm shining a blue laser on a cyclohexane liquid here. So this is the laser beam, and this is the reflection. It's not the beam. This is the beam. And now I put a filter, blue filter. I see yellow emission, right? So this is the Raman scattered light, basically. Right. So this I can see, and I can plot the intensity to get the Raman field. So this is the laser frequency, and this is my Raman frequency. And 1 in a billion light only gets Raman scattered. It's a very small scattering cross section, right? But now I have a crystal here. This you will not study in your English textbook. Okay. So this is a crystal. What is this? This is a silicon crystal. Silicon is used as in semiconductor industry. Right? Now, if you do Raman, you find only one sharp peak. Why is it? If I put light into it, what will happen? It will start vibrating bonds. So one vibrating bond will influence the other vibrating bond. So it will travel. The vibrations will travel like waves. So those are called phonons. Remember phonons? Okay. So then, how light scatters with that phonons gives you this peak. Okay, or the change of energy. So this has to do with the conservation of momentum of the light. Because there is a vibration, phonon vibration. So phonon is a vector. It has a direction and a magnitude. And then your light also is a vector. So then you have to do the calculation and find out how much of energy exchange with phonon is there. Okay, and the collected light, scattered light, will lose some of the energy and will give you this peak. So this intensity of this peak is light which has lost some of its energy to the vibrations in the system, right? So then this is more stuff. So read this in solid state physics or chemistry. So you can actually plot the energy or the vibrations of these phonons of the vibrating atoms into this dispersion diagrams. So this has a vector, this is reciprocal space, and these are the frequencies. So these are the frequencies which can happen in a crystal. Right? I'm not going into details, just giving. So what happens is I am putting light into the crystal and seeing the scattering, right? Now what will happen is the vibrations which are there in the crystal and my light, so the light, actually the frequency of the light determines which vibrations it will interact with. Okay, because for example you cannot put a big boulder and a pin and study the change of energy effectively, right? So you need to have two similar balls to play around with, right? So conventionally, this is the Brillouin zone's center. Okay, so there is a Brillouin zone in a reciprocal lattice. You just don't have to get bothered too much, but we get vibrations very near to the Brillouin zone of the reciprocal lattice by using visible light. So if you see here at this particular zone, I have a frequency at around 520 meters. And at this zone, nearby this zone, there are no other frequencies. There are frequencies of 0. So then, corresponding to this frequency, I see a peak here. Okay, so these are like the vibrations, lattice vibrations, which I am probing with light. So there is a lot of physics behind it. I'm just giving you a flavor. You can go and read the book of Charles Keeton, Solid State Physics. You will find this thing. Okay. So now, because it probes vibrations in crystals, I have one particular material. Okay. Like glass. Glass can be either crystalline quartz glass, it can be fused quartz, or it can be just a normal microscope glass or a window glass. But the Raman spectra looks very different. Why? Because the lattice vibrations are different. Because in the amorphous phase, so this is crystalline quartz, and this is totally amorphous. So there is a loss of long range order. So I am probing now the entire. So if there is a loss of long range order, I am probing the entire frequency space. So my peaks become very broad. Okay, so what happens is this gives us some idea about crystallography also. So remember, Raman was working on scattering using light, but indirectly he was also influencing crystallography. So that's why some people also call it Raman crystallography. Okay. Okay, so same thing, I have a single crystal of silicon. Now if I bombard the silicon vapor with ions, it becomes broad. Because then it's losing its long range order, and I am probing the entire frequency space of the crystal. Right? So another thing which Raman worked himself, and is very important, is diamond. So diamond is a very interesting material, right? It's the hardest material available. It has a interpenetrating FCC lattice. You know about lattices, right? Face-centered cubic and all. I think you learn in NCERT books also nowadays. How do you test the Raman? Test the diamond, whether it's pure or not. Okay, so believe it or not, Raman is one of the most reliable techniques, even used by jewelers. In like this Raman is a very expensive instrument, used by jewelers to assess the purity of the diamond. See, this blue is the spectra from the pure diamond, one single key. And these are all glass imposters, American diamonds. They are hugely different keys. Just take one Raman spectra, it takes 2 seconds to collect one Raman spectra, and you get your purity of the diamond. Okay. So this study was done by students of Raman himself and published. Okay, they were the first to study the Raman spectroscopy of diamond. If you see the crystal space here, like the dispersion diagrams here. So you see here, this is the Brilva zone center, and you see 1328 centimeter inverse, you get one single key. There are no other frequencies present with the Brilva zone center. So this is the story of diamond. So Raman was fascinated by diamond, okay, and not only diamond, Raman can be used to study, it's one of the most important instruments to study carbon materials. For example, can you tell how many layers of graphene? You know graphene, right? Single. It is used to measure the number of layers of graphene. I didn't show the physics here. It would be crazy. So this is a modern Raman spectrometer. We also make it in our lab. You get it in this one. We also make it in the lab also. Okay, so one of the most important things which Raman didn't have was what? Laser. So that time he used sunlight. But when did lasers come? Late 60s, 70s, right? We have lasers, highly monochromatic, 400 beams, right? So we can study a lot more materials than Raman could. Okay. So now there are a lot of variations of Raman. Okay, surface enhanced Raman. A lot of. I'm not going. And a lot of applications in chemistry, pharmacy, cosmetics, food, agriculture. New applications are coming up basically. So one of the very famous, or very popular thing is surface enhanced Raman spectroscopy, where you use. It's a combination of Raman spectroscopy and nanotechnology. So you use gold, silver, copper nanoparticles to trap light, capture light, and then increase the scattering cross section of the Raman. Okay. So I'm not going into details, but it kind of, you say that I get a Raman, very weak Raman scatter. Using this technique, I can enhance it 1 lakh times. Okay, so it's pretty interesting. So these are some of the plasmonic substrates or nanostructure substrates we make to enhance the Raman signal. So these are my papers only of my research. Okay, so you see some very nanoscope structures. Okay, so for example, I made this silver nanostar or nanoflower kind of thing, and we kind of used it for ELISA detection. Okay, for HIV using Raman spectroscopy. So that was pretty neat actually. So Raman spectroscopy, like surface enhanced Raman, has also helped in even understanding how drugs bind to proteins. Okay, to find drug targets. For example, we had this molecule, okay, and it was supposed to bind to 2 different proteins of very similar structure. But from Raman spectroscopy, we showed that this drug, how it binds to only one of the proteins here. It also could tell us the drug binding site. Okay, so that was pretty interesting application of Raman spectroscopy to identify where drug molecules, how drug molecules work, and how it interacts with proteins. Okay. So this is one of our own work, and then you can use these Raman labels, okay, surface enhanced Raman labels. You can target different places in your cells. You can do a cell imaging. Okay, it gives different signature. You can also do a label-free imaging of cells to study different, mechanisms of how cell or how drugs work or different things. You can study cells, biology. So you get a lot of a wealth of information from the different modes in Raman. Okay, so this is something which many people will also understand nowadays. So there is a lot of integration of machine learning nowadays with Raman spectroscopy. So because if you take, for example, a cell, just how many molecules are there in a cell? Billions of molecules, right? Now you are getting the Raman spectra as a whole. How will you understand that this spectra came from protein, or this is from lipid, or this is from ATP? Okay, so for that, what you have to do is you have to use little advanced machine learning, or what we call chemometrics. Okay, so these are some of the classifiers. So I think again AI enthusiasts will know. I'm not going to. We also do principal component analysis to break up the components. Okay, so we can actually classify different samples which have very similar Raman signature. So AI is now playing a very big role in analyzing Raman data. So for example, this is the neural network. So these are some of my activation functions I can choose. I can use the Raman data to train a data set, Raman data set to train an algorithm. Okay, and then I can do some prediction. For example, I have a system, okay, and I can actually use the training or CNN or ANN kind of machine learning algorithms to say that, okay, I have my Raman spectra of a brain, for example, or some tissues or something. Okay, so this component gives me this key. This component gives me this key. Okay, so it's playing a role big time. AI is playing a big role in Raman spectra. So it is, for example, this is also principal component analysis or advanced statistics, which is used to see different parts of the living cell using Raman spectra. Okay, so this is the final thing I will say today. So this is another of our work which were published in Nature. So this was a combination of chemistry, Raman, and machine learning. Okay, so how do you do that? We made probes. Okay, very nicely using click chemistry. So these probes become nanoparticles when they cross the cell membrane. So it becomes nanoparticles once they go into the cells. And these nanoparticles are very highly Raman active. Right? They give beautiful Raman signatures. So we could image cells, and then also we injected these probes into preclinical models like rats, and then we did Raman spectroscopy. So this is Raman spectrometer probe. And using machine learning algorithms, you could actually classify whether. So these nanoparticles are formed only in cancer cells, not in healthy cells. So we made this kind of one platform where you can actually use this Raman spectroscopy and chemistry to do cancer imaging live animals. So this is pretty interesting. So coming back to Raman didn't have lasers, otherwise maybe he could have done all these things himself. Maybe. But he was a very admirer of nature, and he did a lot of research in his later days on human sight and colors. There's a lot of papers. Okay. So, but one important discovery when he was in IASC was Raman-Nath effect. How many of you heard about Raman-Nath effect? So, okay. So this Raman-Nath effect is nothing, but you have seen this prism, right? It disperses light. So instead of a prism, what they did was they took a column of liquid or fluid, and then they passed sound waves. So sound wave is like longitudinal waves, right? Compressive distance. So this is creating ripples inside, right? Like changes in maybe transient changes in refractive index in the. So they use this pattern to deflect light. Amazing, right? This is these two are very seminal papers of Raman. Now, the most advanced microscope optics is using something which is called acousto-optic filters. Have you heard of this name? You might not have. This is state of the art. Now, it's very expensive, this filter. Now they are developing this using effect which was published by Raman.
So we do ultrasonic plating experiment in the lab. Doesn't we don't get results.
Okay. You need to have that experimental hands. I say you need to make your experiment.
Yeah, so I will get motivated by what people said. Good hand and then lower the price.
You see how he directed the sunlight in his room. You see, like, how is he going to do that, right? Anyways, I just want to end with this that C.V. Raman was a person with whom anybody interacted used to get motivated. He was amazing science communicator, and he started this Gandhi Memorial Lecture like every year on 2nd of October. He used to give this lecture to kids about research. Okay? And he was a very big admirer of Gandhi also, because in his Nobel lecture he said that the great man is still in jail. Okay, so it's pretty amazing. This was the Raman Research Institute which he built, and this was actually his last photograph. It was taken on incidentally mostly on 2nd October after his lecture in 1970. So he had some heart disease and issues. So he sadly passed away because of the heart. So this was what he said, that India could progress only through science and more science and still more science. So yeah, happy Science Day to all.
Now open the floor for Q&A. Please raise your hand if you wish to ask something, and we'll pass on the mic. Do you wish to ask anything?
Everyone understood everything.
I'm just curious. The spectrometer that is kept at RRI, which they claim, is it actually the real one?
Yeah, so it's not in RRI, it is in IAC. It is kept
The one that is kept in RRI. It's in RRI.
No, it's in IAC. The wooden one,
Yeah.
the original one. Yeah, that is the real one.
Is it the
Yeah, and incidentally, that is not kept in IICS in Calcutta where it was discovered. Yes. Yeah, I have seen that in
No, so
IICS.
real one means, was it the one on which he actually did his seminars was for which he got his?
Yes, yes. Yeah, I have shown that.
Oh, the one the bit.
Yes, yes. You can see that. It's
Yeah, I've seen it. I thought I saw it in RI, but I think I missed it.
in RNI, he has a museum where he kept all his hammer, yes, and all these things he did his experiments.
It was actually lecture for occasion. And I saw that everything I thought maybe we would do technical and things like that.
Yeah, so when I heard that it was like for all three societies, then I thought I should have something for everyone and also maybe.
But you've encouraged us enough to come and see the.
You're always welcome. Anytime you're welcome, just drop me an email or a message and just sound. So I'm also a part of the outreach of IIT Delhi, and we are actually organizing a big event on 22nd of March, which is commemoration. We are calling all the UG students for the first time in NCR.
So when you said you make them in your lab, you actually design the spectrometers yourself. So are they low cost?
We try to make it low cost.
You try to. Is it affordable?
See, okay. So this is kind of a trivia. So you have this Ferrari, right? And you have this this light one very short. It's a UK company. They make very good Raman spectrometer. So I have a Ferrari. I have a Raman spectrometer which one costs more.
You actually have a Ferrari?
Ferrari will cost like 1 crore maybe. This particular machine here on the screen is 2.5. No, I don't have in my lab because I'm still not that rich. But we have in our institute. But I have made one Raman spectrometer in our lab for less than 25. So I get to the picture here because similar patent process. So anyways, this is.
How did the ICCS and Raman Bangalore everything went into Bangalore?
No. By that time he left ISCS, it was already established. Like so many. Yeah. So he established ISCS and still it is running so well. It's one of the still it is one of the premier institute in India, research institute. So yeah, he was an institute visitor kind of. So I also came to know a lot of his life stuff preparing for this lecture. I knew the science part, but I came to know about other parts of his life also. So it was very nice.
So I wanted to ask that why does the polarizer reject the reflection of light? Why does it reject that?
So basically the reflected light is not polarized. So non-polarized light is like has polarization in all directions. So it just blocks. So and polarizer allows the only one direction polarized light to pass through. Okay, so basically it blocks out the entire all the other polarized light, but polarized in other directions. Okay, so that's why you lose the almost bulk of almost like more than 99% of the reflection.
Yes, sir. And also you said that light is a vector, phonon and light is a vector. So how can we interpret that light is a vector? Like the physics that I am studying, till now, what we use that we just write C and we do not use any vector notation about that. We just write C.
Is just the magnitude, you know, just the speed of light. Okay. So if you're talking about light, you have to think it in terms of electromagnetic wave. So E is E naught is equal to what? Like it's a cosine or sine wave, right? So then it has components in x, y, z directions. So you can actually have a matrix for a particular electromagnetic wave.
Okay.
You think it's that way, then you will do it.
Any more questions? Thank you so much, sir, for the wonderful lecture.
Now, I would like to call Dr. Vibhav Sharma, the head of department, the head of chemistry department, to present a memento as a token of gratitude to Dr. Swami Siddhanta.
As we celebrate the intellectual spirit of our societies, it is an honor to launch our annual journals and newsletters, each showcasing the research, discussions, and achievements of the past year. These publications stand as a reflection of our commitment to knowledge and exploration. I now invite Jasmine Babu and Anushi Srivastava, journal heads of the Physics Society, to unveil ECHO, the annual journal of the Physics Society, and present it to the staff advisor, Dr. Harish Kumar Yadav.
So much hard work for their time. Okay, I think
Thank you, sir. Thank you, Anushi. Thank you, Jasmine.
Next, I invite Shreya Rawat, Oxygen Editor-in-Chief of the Chemistry Society, to launch the biannual journal, Megaphone, and present it to the staff advisor of the Chemistry Society, Dr. Jyotirmoy Maiti, and head of the Chemistry Department, Dr. Prakash. I also request Shreya Rawat to present the memento to the head of the Chemistry Department, Dr. Vibhav Sharma. Thank you, ma'am. Thank you, Shreya. Finally, I welcome Jordan Gabriel, Vice President of the Mathematics Society, to release the exclusive edition of Convergence, the newsletter of the Mathematics Society, and present it to the staff advisor, Dr. Jaspreet Kaur, and the head of the Mathematics Department, Dr. Archana Chopra. I also request Jordan Gabriel to present the memento to the head of the department, Dr. Archana Chopra. Thank you, madam. We have also made a small documentary that showcases the legacy of our society over the decades. We will present the same in our social media platforms.
Now I would like to call Nilasha Fiona Mascarenas, President of the Physics Society, to give the word of thanks.
Hello everyone. As we bring to a close to this momentous 50th anniversary Science Conclave, it is my esteemed privilege to express our deepest gratitude to each one of you present here and has contributed to making this event a resounding success. First and foremost, we offer our sincerest appreciation to our principal, Dr. John Burgess, for his unwavering encouragement, which has been catalyst that has made today's success possible. We extend our gratitude to Dr. Somik Siddhanta for his enlightening lecture on Raman spectroscopy, a vibrational adventure. Your talk has not only broadened our understanding but also inspired us to explore the vast expanse of the scientific knowledge. And our heartfelt thanks to our generous sponsors whose contribution have been instrumental in making this event a success. We particularly are grateful to Group Captain Joshua Emanuel of the Indian Air Force, esteemed alumnus of batch of 1993 for his contribution, which has been a cornerstone of our sponsorship. I would also like to thank Mr. Ravi Sachdeva, a distinguished alumnus of batch of 1974, and Mr. Deepak Kumar Singh, batch of 1993, for their contribution which has enabled us to provide a memorable experience to our participants. We extend our gratitude to our faculty members, ROS, Dean, for their presence and encouragement. Our staff advisors deserve a special mention for their sage guidance and unwavering support. Your patience, expertise and dedication have been invaluable in shaping this event into a resounding success that it has become. To the council and volunteers of all three societies, your selfless dedication, creativity and perseverance have been a driving force behind this conclave's time. Last but not the least, I extend my warmest gratitude to the presidents of Mathematics Society and the Chemistry Society for their collaborative spirit and tireless efforts in organizing this milestone event. It has been an absolute pleasure to work together in bringing this vision to life. And to our audience, we thank you for your enthusiastic participation and engagement. Your presence has made this event all the more special and we are honored to have the shared experience with you. As we bid adieu to this momentous celebration, let us carry forward the torch of scientific curiosity, collaboration and innovation. Thank you once again and we eagerly look forward to many more celebrations of science in the years to come. Thank you.
With that, we officially conclude the inaugural lecture. I would like to request everyone in the audience to kindly gather in the science class for a photograph, some light refreshments. Additionally, there are desks for students to mark their